Hi friends, welcome to my channel. Before going to the video, those who are not subscribed our channel, subscribe it and also click the bell button. In this video, we are going to discuss about semiconductor lasers. As we already know, laser stands for light amplification by stimulated emission of radiation. Semiconductor lasers are specifically fabricated p-n junction diodes which emit laser light when forward biased. They are often made of gallium arsenide because gallium arsenide is a direct bandgap semiconductor. In direct bandgap semiconductor, there is a large possibility for direct recombination of holes and electrons, thereby emitting a photon. But in indirect bandgap semiconductor, the recombination of hole and electron is not possible. Hence, there is no photon emission. Hence, gallium arsenide, which is a direct bandgap semiconductor, is commonly used to make LEDs and lasers. Laser diodes are made of degenerate semiconductors to create the condition of population inversion, which is the basic principle of laser. Degenerate semiconductors means semiconductors which have high level of doping so that they act more like a metal than as a semiconductor. The degenerate semiconductors are often used in integrated circuits as a replacement for metal. Next is the properties of lasers. Laser generates monochromatic coherent light which reduces chromatic dispersion. Monochromatic light means light of single wavelength, that is single color. Coherent light means the emitted light will have same frequency, that is the photons will have same frequency, same phase, same momentum vector and same polarization. Next, the laser beams are very powerful than high power ordinary light beams. They have high directivity of optical output, high intensity and high quantum efficiency, that is high output power. Lasers have narrow spectral bandwidth than LEDs. Their lifetime is shorter than LEDs and also they are more sensitive to temperature than LEDs, that is light emitting diodes. They have high emission frequency and high data rate. They are costlier than LEDs and hence they are used only for high power long distance optical communication. They are not used for short distance optical communication. Next, let us see in detail about coherence. Coherence is the phenomenon in which the emitted photons will have same frequency, same phase, same momentum vector, that is both direction and magnitude, and same polarization. This coherency is an important characteristic required for optical communication. Next, coherence length. It is the propagation distance from the coherent source to a point where the electromagnetic wave, that is the light, maintains a specified degree of coherence. Within this coherence length, the electromagnetic wave is similar to a perfect sinusoidal wave. The formula for coherence length is L is equal to lambda square by del lambda. Here lambda is the wavelength of the emitted radiation and del lambda is the spectral line width. The coherence time is given by tau is equal to L by C. L is the coherence length and C is the velocity of light. There are two types of coherence, temporal coherence and spatial coherence. The temporal coherence explains us about the behavior of amplitude of the electric field of the electromagnetic light wave as a function of time. Spatial coherence explains the behavior of the amplitude of the electric field of the electromagnetic wave in a plane perpendicular to the direction of propagation as a function of space. Next, if you consider a semiconductor material, an electron occupying a higher energy level is said to be in the excited state and the electron occupying a lower energy level is said to be in the ground state. And also an electron in the excited state has a tendency to release the extra energy and come down to the ground state, that is the lower energy level. Now let us consider a system with two energy levels E1 and E2 and E2 greater than E1 in a semiconductor material. E1 and E2 are the energy levels. E2 is the higher energy level, E1 is the lower energy level. A radiative recombination between these two energy levels will correspond to a photon emission, and this photon will have energy E phase EPH, which is given by EPH is equal to E2 minus E1, which is equal to H into F, which is equal to H into C by lambda, since frequency F is equal to C by lambda. C is the velocity of light, lambda is the wavelength. Here, if N1 and N2 are the thermally generated electron densities at E1 and E2 respectively, then N1 by N2 will be equal to e to the power H into F divided by KT. Suppose if the wavelength of the emitted photon is 0.7 micrometer at room temperature, that is 300 Kelvin, then EPH, that is the energy of photon, will approximately be equal to 3 into 10 to the power minus 19 watt second, and N2 by N1 will be approximately equal to 1 by e to the power 100, which is approximately equal to 10 to the power minus 32. From this equation, we see that the density of electrons in energy 2 E2 for a photon of energy corresponding to 0.7 micrometer is almost negligible, which suggests that at room temperature the higher energy levels are almost empty and unoccupied by electrons as compared to the lower energy levels. Next, let us see the phenomenon of light emission in semiconductors. In semiconductor materials, the photons are interacted with the atoms in the semiconductor by three ways. First is the spontaneous emission, second is the absorption of radiation, third is the stimulated emission. First, we will see in detail about spontaneous emission. The transition of an electron from higher energy level, that is excited state, to lower energy level, that is the ground state, can take place as a result of natural tendency of the electron, that is without any external agent or external stimuli. This emission of radiation as a result of such transition is called as spontaneous emission. The rate of spontaneous emission is given by minus dN2 by dt, which is equal to A21 into N2. Here N2 is the electrons per unit volume or electron density in the excited state, that is higher energy level. The solution of this differential equation is given by N2 of t is equal to N2 of 0, that is electron density at 0 time, into e to the power minus A21 into t. This is also equal to N2 of 0 into e to the power minus t by tau sp. Here tau sp is the average lifetime of an electron in the excited state before its spontaneous transition to the ground state takes place. Its value will be equal to 10 to the power minus 8 seconds. Next is absorption of radiation. When light is incident on a semiconductor material, some photons get absorbed in the material. These photons transfer their energy to the electrons in the ground state, that is lower energy level, and cause them to migrate to the excited state. This phenomena is called absorption. The rate of absorption of radiation is given by minus dN1 by dt, which is equal to B12 into N1 into rho of F. Here N1 is the electron density in the ground state, that is lower energy level. B12 is the Einstein coefficient. Rho of F is the incident photon flux density function. F is the frequency of emitted photon. Next is the stimulated emission. When the semiconductor material is externally incident with photons, the electrons in the exciter state jump down to the ground state by releasing the excess energy in the form of radiation, that is photon. Here, the externally incident photon does not get absorbed by the semiconductor material. It just initiates the generation of new photon. This is called stimulated emission. The rate of this stimulated emission is given by minus dN2 by dt is equal to B21 into N2 into rho of F. Here N2 is the electron density in the excited state, B21 is the Einstein coefficient, rho of F is the incident photon flux density function. The figure shows the three phenomena that takes place in the semiconductor material, that is the absorption of radiation, spontaneous emission and stimulated emission. In absorption of radiation, when an external photon is incident on the semiconductor material, it causes the electrons in the ground state to jump to the exciter state, that is higher energy level E2. In spontaneous emission, the electron in the higher energy level E2 spontaneously, that is due to its natural phenomena, it jumps to the ground state E1 and emits photon which move in random direction. It does not require any external photon for stimulating the process. In stimulated emission, an external photon is incident on the semiconductor material and the electrons in the higher energy level E2 jump down to the lower energy level E1, thereby releasing photons which move in the same direction. At thermal equilibrium, the electron densities in the two states have to be maintained, and so the total number of emissive transitions must be equal to the total number of absorptive transitions. Hence, B12 into N1 into rho of F is equal to A21 into N2 plus B21 into N2 into rho of F. Rearranging the above equation, we obtain the expression for photon flux density function as rho of F is equal to A21 by B21 whole divided by B12 divided by B21 into N1 by N2 minus 1. This equation gives us the net photon flux density emitted from the system when the three processes absorption, spontaneous emission and stimulated emission takes place simultaneously inside a material. Next, let us see the difference between spontaneous emission and stimulated emission. First, spontaneous emission is a naturally occurring phenomena, but stimulated emission is not a natural phenomena. It has to be initiated by external agent. Spontaneous emission does not require any external photon as a stimulus, but stimulated emission requires external photon as a stimulus. In spontaneous emission, the light has less intensity than stimulated emission and it is incoherent. But in stimulated emission, the emitted light is highly intense, monochromatic and coherent. In spontaneous emission, the emitted photons have random motion, but in stimulated emission, the emitted photons move in the same direction and they have high directivity. The spontaneous emission phenomena occurs in LED. The stimulated emission phenomena occurs in laser. Next is population inversion. Population inversion is the state in which the number of electrons in the higher energy level is more than those in the lower energy level. Generally, more number of atoms are in lower energy levels. When a photon having energy equal to the energy difference between the two levels of atom is incident, then the probability of getting absorbed is more because the lower energy level have more electrons. But in population inversion state, the probability of photon causing stimulated emission is more than absorption because more atoms are in higher energy level, thus causing amplification of light. Hence, population inversion is an important principle in laser so that stimulated emission is more probable than induced absorption. The first figure shows the normal state in which the energy level E1 has more number of electrons than E2 and E3. That is, the higher energy levels have low number of electrons, and lower energy level have high number of electrons. But in the second figure, population inversion state, the second energy level have more number of electrons than the lower energy level E1. Hence here the probability of stimulated emission is more than the absorption of radiation. The population inversion state can be achieved by the following ways, that is optical pumping using the light source, electric discharge or excitation by electrons, inelastic atom to atom collisions, thermal pumping and chemical reactions. Next is Excimer laser. Excimer or Exciplex laser is a form of ultraviolet laser which is commonly used in the production of microelectronic devices, semiconductor based integrated circuits, that is IC chips, photolithography, eye surgery and micromachining. This Excimer laser uses a compound or diatomic molecule of noble gases, halogen, etc. as its laser medium. The table shows the wavelength of different Excimer lasers. Here if you see, argon has the lowest wavelength of 126 nanometer, krypton has 146 nanometer, fluorine have 157 nanometer, xenon have 172 and 175 nanometer, argon fluoride have 193 nanometer, krypton chloride have 222 nanometer, krypton fluoride have 248 nanometer, xenon bromide have 282 nanometer, xenon chloride have 308 nanometer and xenon fluoride have 351 nanometer, which is highest wavelength. Next, let us see the previous year questions. First question, this question was asked in June 2014. Consider the following Excimer lasers used for photolithography and surgery purposes. First, argon Excimer laser, argon fluoride, xenon chloride, xenon fluoride. The correct sequence of the descending order of the wavelength of operation is, here we know that xenon fluoride has the highest wavelength, then xenon chloride, then argon fluoride, then argon. So option D is correct. Next question. This question was asked in June 2014. It is match the following type. First, laser. We know that laser emits monochromatic light of high intensity. Next, solar cell. It delivers power to load. Next, photodiode. It consumes electrical power due to the incident light. Next, LED. It emits monochromatic light of low intensity. Hence, option C is correct. Next question. This question was also asked in June 2014. It is assertion and reason type. Optical fibers have broader bandwidth compared to conventional copper cables. Reason: low power laser beams are considered to be very powerful as compared to high power ordinary light beams. Here Both the assertion and reason are true, but the reason is not the correct explanation of assertion. Next question. This question was asked in December 2014. Assertion. The two types of optical fibers are used in transmitter of optical communication link are LED and laser. Reason. Lasers are costly and hence not preferred for small distance low cost systems. Here we know that the two types of optical sources used in optical communication are LED and laser. So assertion is correct. But the reason, if you see, lasers are costly and hence they are not preferred for small distance low cost system. We know that it is preferred for long distance systems. So reason is also correct, but it is not the correct explanation of the assertion. Next question. This question was asked in December 2014. The following are correct about a semiconductor laser. It requires population inversion. It has shorter lifetime than LED. It demonstrates spontaneous emission phenomena. It generates monochromatic incoherent light. Find out the correct answer. We know that semiconductor laser requires population inversion. It has shorter lifetime than LED. But the statement 3 and 4 are wrong because it requires stimulated emission and also it generates coherent light. So option A is correct. Next question. This question was asked in December 2014. In compared to LED, laser has high emission frequency, no tuning arrangement, narrow spectral bandwidth, provision for confinement of this. Find out the correct answer. We know that laser has high emission frequency and also narrow spectral bandwidth than LED. So 1 and 3 are correct. That is option C is correct. Next question. It is match the following type. It was asked in December 2014. First, LED. We know that spontaneous emission takes place in LED. Next, avalanche photodiode. It is related to current gain. Next, tunnel diode. It is heavily doped. Next, laser. Laser, it gives coherent radiation. So option C is correct. 8th question. This is also match the following type. It was asked in July 2016. Photodiode. It exhibits increase in reverse current with light intensity. Laser. We know that it is made of degenerate semiconductors. Next, solar cell. Power consumption is negative. Next, optocoupler. It prevents high voltages from affecting the system receiving the signal. Next question. This question was asked in July 2016. Assertion. In lasers, the photon's emitter has the same energy as the incident photon and in phase with it. Reason. The amplitudes of individual photons add to produce a brighter light. Here we know that both the assertion and reason are true, but the reason is not the correct explanation of assertion. Next question. This question was asked in Jan 2017. Which of the following condition is applicable in semiconductor lasers? If you see in semiconductor laser, the energy difference between the Fermi level of conduction band and Fermi level of valence band will be greater than the band gap energy. So option B is correct. Next question. This question was asked in Jan 2017. Which of the following statements are incorrect in case of semiconductor lasers? Stimulated emission rate dominates the spontaneous emission with increase in the value of energy of radiation per unit volume per unit frequency. Stimulated emission rate dominates the absorption rate if the charge carriers in the ground state are higher than the excited state. Lasers have a longer lifeline than LEDs. Laser diodes are more temperature sensitive to LEDs. Here they are asking the incorrect statement. First statement is correct because stimulated emission rate dominates the spontaneous emission rate with increase in the value of energy of radiation per unit volume per unit frequency. But if you see the second statement, They have given stimulated emission rate dominates the absorption rate if the number of charge carriers in the ground state are higher than the excited state. It is wrong, because if the number of charge carriers in the ground state are higher, then absorption rate dominates the stimulated emission. And also, if you see the third statement, the lasers have longer lifetime than LEDs. It is also wrong, because they have shorter lifetime than LEDs. And fourth statement, laser diodes are more sensitive, temperature sensitive to LEDs. It is also correct statement. So only 2 and 3 are incorrect. So option D is correct. Next question. This question was asked in November 2017. A certain helium neon laser emitting at 633 nanometer has a line width of 0.002 nanometer. The coherence length of the laser is given by. We know the formula for coherence length of the laser as L is equal to lambda square by del lambda. So substituting for lambda wavelength as 633 nanometer and line width del lambda as 0.002 nanometer, we have the coherence length as 20 centimeter. So option C is correct. Next question. This question was asked in June 2019. Which of the following are advantages of laser over LED? Higher bandwidth and higher data rate, higher output power, longer lifetime, cheap. We know that lasers have higher bandwidth and higher data rate and higher output power, but they have shorter lifetime and they are costly. So only 1 and 2 are correct. Hence option B is correct. Next question. This question was asked in December 2019. Consider the following statements. Laser diode generates monochromatic coherent light which reduces chromatic dispersion. Laser source is useful for high power long distance optical communication. Lasers have longer lifetime than LEDs. Laser diodes are less temperature sensitive than LEDs. Select the correct answer. We know that laser diode generates monochromatic coherent light which reduce chromatic dispersion. So statement 1 is correct. And also they are used for high power long distance optical communication. It is also correct. But if you see the third and fourth statement, it is wrong, because lasers have shorter lifetime than LEDs and also they are more temperature sensitive than LEDs. So only 1 and 2 are correct. Hence correct. Thanks for watching the video. For more videos, don't forget to subscribe our channel.